All right, ladies and gentlemen, boys and girls, welcome to another fantastic episode of Space Nuts, the podcast that is out of this world. I am your host for this week, Heidi Campo, here back again with the commentary and the jokes. I know I am not your beloved Andrew Dunkley, but I promise I will continue to do my best.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
But hey, the best part of the show is right here with me, Professor Fred Watson, astronomer at large. How are you doing today, Fred?
Pretty well, thank you. It's a very bright morning here in Sydney, and the sun is shining, and it's a nice crisp autumn day, if I can put it that way, which I know makes no sense in the United States of America, but it's an autumn day.
That's okay. I'll give you our weather report over here from Space City, Houston, Texas. It's a beautiful spring afternoon. It's later in the day here. We have had a really fantastic week. The birds are chirping, the flowers are starting to bloom, but it's about to start really heating up. So I think it's going to start creeping up to 90, and it's not gonna go down until few months from now. So we're going to have a nice hot summer as usual.
What a surprise.
Yeah.
Yeah.
So here's a interesting thing that I learned recently from a friend of mine who's a flight surgeon. We were at a conference. We were actually at the Spaceflight Human Optimization and Performance Summit this time last year. And I was sitting there freezing cold. And I asked her, I was like, why is it always so cold when you go to conferences? Every conference I've ever been to is freezing cold. And she looks at me and goes, oh, well, there's a reason for that. When they keep the conference rooms cold, it helps prevent the spread of germs. And I was like, really? They do this on purpose? And I thought that was super interesting that there's a reason for it, and they don't want to just make all the attendees miserable. It's all about, preventing the spread of germs. Did you know that?
No, I always thought, I agree with you. We were in a conference a month ago in which the auditorium was cold, and we were all sitting there well wrapped up. I just assumed it was so that the delegates didn't fall asleep. That's why I thought it was cold, so that you keep everybody awake, miserable. But yeah, the spread of germs sounds a lot more, a lot more important, in fact.
Yeah. And speaking of germs, it's something to really consider when we're up in space. I mean, the astronauts have to go through vigorous health testing before they go up on the shuttle. And then when they are up on the space station, there needs to be a way to keep track of what little microbial hitchhikers went up with them. And that looks like something that China is really been working on lately with, it looks like a microbial map is something that they've been coming up with.
Yeah, the reason I thought this story was interesting, and you're quite right, this is the microbial profile of the Tiangong Space Station is being mapped with a program. I love the acronym. It's CHAMP is the acronym. It's the China Space Station Habitation Area Microbiome Program, and that sounds very much like an acronym that was chosen and then the word strained to fit into it, like most acronyms are. But the reason why I thought it was an interesting one is that we had a story, it's probably about a month ago, which was commenting on the return of one of the recent crews from the International Space Station, and it was probably, I don't know, I think it was probably late last year, who fell mildly ill on their return to Earth. And I can't remember which crew it was or what. And I think we ever found out what their illnesses were, just as it's a privacy thing. But the comments that were coming after that from people who know a lot more about this sort of thing than I do, was that the International Space Station may be too sterile. It may be an environment that does not have its own sort of microbe population. And there were suggestions being made, like 2 or 3 dogs or cats up there might kind of help, with de-sterilizing it a bit and make it an environment that is not detrimental to astronauts. If everything's too sterile, yes, you're not going to get infected with anything, but you might get ill when you get back down to Earth. And that was the thing, that I thought, well, it's interesting that the other space station, and there are only 2 at the moment, the Tiangong Space Station, which has its own set of experiments and things of that sort, they basically have this program that goes into the genomics of the microbes that are there. They've gone into great detail about probably the microbial species. They've investigated how well these microbial communities evolve, how well they replicate, and essentially how well they adapt to microgravity. Now, I'm sure there have been experiments like this on the ISS as well, because one of the main thrusts, as you know, as a space medical person, one of the main thrusts is how humans behave in the environment that we put them in on the space station. But I suspect we haven't heard quite as much about it as what we're hearing in this research report that has come out. It is called. The research report is an early microbial landscape, inspiring endeavor from the China Space Station Habitation Area Microbiome Program, or CHAMP. And it comes from the Shenzhou Space Biotechnology Group. So it just struck me as being an interesting insight into how China is approaching this issue of microbes in space.
And it really is so interesting to think of, a space being too sterile. And I always just think about, like with our food. And I think back to a conversation I had years ago. I was at the farmer's market and I was purchasing, I think it was just like lettuce or something from a farmer, and there was a little bug on it. And I was like, ooh, a bug. And the farmer looked at me with the sweetest, kindest look and smile. He was one of these farmers who just like, they're just a good human. And he looks at me and he's like, if there's a bug on it, that means it's probably good for you. And it's not full of all that other bad stuff. And I was like, it's like, if the bugs want it, he's like, your food is and he went on to this whole spiel about your food is life, and our gastrointestinal systems and our entire body and our own microbiomes that live on us is a very symbiotic relationship between us, our food, the environment around us. And if you sterilize everything from the food that the astronauts are eating and their spaces around them, there's a very delicate balance of our microbiomes that we need and live in and on and around us that potentially need to interact with the ecosystem outside of us as well, that disappears when they are up in space for that long.
Yeah, quite remarkable. I mean, you can understand why you would want a sterile environment in space, just to try and keep people healthy. But if in doing that, you're totally destroying this symbiosis that you've mentioned, then people are going to get sick, and that might be what has happened. I think you've talked to astronauts, Heidi, in the past. Has any of them commented on how they felt when they returned to Earth, whether they did feel as though they had any deleterious effects in terms of their things like digestion and things of that sort, I guess?
I think the conversations I've had in either interviews or casual conversations is just really they give me kind of the HR answer because I don't. So just to be clear, I don't work at NASA, and I'm still just a student working in exercise countermeasures in human spaceflight and optimization. So I'm not quite as deep in as I'd like to be yet. But from what I have heard, at tertiary level, is they do feel a little bit crummy when they come back, and it takes a little while to adjust to being back here on Earth. And some of that, it's like, think about like a sailor. Like, it takes time. Like, they get their sea legs on the ship, and then when you get back, you're like, man, it's like adjusting to any different ecosystem is gonna kind of alter you a little bit, but Sunny, she's doing great. She's back. I guess she's doing her fitness classes again. She does CrossFit, which I don't know if I agree with, but that's a topic for another time. But doing the things that are part of your regular routine and getting you back to your regular routine should be the priority, because that's where your body is going to be the happiest. And so if we can figure out a way to kind of create that environment up in space, even on a bacteria level, they're going to be so much better at adapting when they get back here, instead of having that stark kind of shift.
It's fascinating stuff, and of great importance, of course, as we contemplate future very long space flights, if we embark on interplanetary travel.
Absolutely. One little kind of a sci-fi tidbit. So for those of listeners who plan on reading Hyperion and don't want it spoiled, you should fast forward 5 seconds. But there is a concept of a tree ship. So they have, in the sci-fi book, they've grown a tree to be so large that it has its own atmosphere and ecosystem, and they use it as a interstellar ship. And then the real big reveal later on in the last book, fast forward 5 seconds if you don't want it ruined, is they create a organic Dyson sphere out of trees, which is a very interesting concept that's very far-fetched, very sci-fi, but so interesting when we're thinking about organic matter in space. And who knows, we might realize that the author of Hyperion was onto something.
Roger, you're loud and clear here also.
Space nuts.
But life in space is something that we are always interested about and curious about. And it looks like there might be something on Titan.
Yeah. Titan, perhaps the most interesting world in the whole solar system after our own planet, of course, and with similarities to our own planet. Very, very briefly, what we have with Titan, the biggest moon of Saturn, and actually second largest moon in the whole of the solar system, bigger than the planet Mercury, an extraordinary world, which has a rocky core overlain by a liquid ocean, probably of brine or at least a very mineral-rich water, on which is a layer of ice, which at the temperature of minus 195 degrees Celsius, I don't know what that is in Fahrenheit. It's very cold. At that temperature, the ice layer over the water behaves just like rock. And so we have this curious aspect of depressions in that surface, which have lakes in them, but not of water. They're of liquid natural gas, methane and ethane, a mixture. And there is a weather cycle on the surface of Titan. Titan has a thick atmosphere. And, you get methane rain on Titan and phenomena related to the weather cycle on Earth. Now, the scientists who have engaged in the study that I wanted to mention, who are from universities in the United States, they are at the University of Arizona and also Harvard, they have been looking at the prospect of living organisms, water-based living organisms, in the sub-ice ocean. And what they've done is they've looked at the transport of organic nutrients, and we've just been talking about organic nutrients on the International Space Station. These are the chemicals, the prebiotic chemicals on which any living organisms might feed. They've looked at the migration of that from the surface of Titan, which we believe is very rich in these organics just because of the chemistry of the atmosphere itself, how that might migrate through the ice layer, which could be something like 450 or so, 300 miles, 450 kilometers or so thick, a very thick layer of ice, how that would perhaps track down into the ocean to feed any microbial organisms that were present in the ocean underneath Titan's surface. And the conclusion they get, which is not that surprising when you think of 300 miles of ice to get through, is that not much comes down there. And so that if microbial life exists in the oceans of Titan, then it would be at very, very low levels. They talking about, I think they said 1 cell per cubic meter or something of that sort, which means that when you add together all the ocean of Titan, you've got enough microbes to make a dog or something of that sort. Not very many. And so this is sort of depressing from the point of view of whether there is microbial life in the ocean of Titan. But what surprised me was that this article paid no heed, and that's because this is not the research of the people who are working on it. This is not their particular topic. But certainly a few other astrobiologists have looked at the prospect for life based not on water, as all life on Earth is, but on liquid natural gas, the ethane and methane that makes up the lakes and seas of Titan on the surface. And I know early on in the Cassini mission, when Titan was first being explored with the Cassini radar and the Huygens lander, which touched down on the surface of Titan, when that mission was in progress, people were speculating about microbial creatures that use methane and ethane as their working fluid. And there were some suggestions that they might breathe hydrogen, which is there on in Titan's atmosphere, and perhaps eat or feed on acetylene, which is a complex organic molecule, which is also plentiful around the surface of the shores of the lakes of Titan. So that's perhaps the alternative view, and it might be a wonky view. I'm not, as I'm always at pains to point out, a biologist of any kind, apart from being a self-taught one. But the idea of a microbial or living organisms generally, which base their existence on a different fluid from water, I think is a fascinating one. And that's why the Dragonfly mission, which NASA is planning to send to Titan, a little airborne vehicle, a bit like Ingenuity on Mars, but a bit more complex and a bit cleverer. That's why the Dragonfly mission is so interesting and which we're looking forward to so much.
That is so cool. I've never quite understood how. I mean, I guess it's just because the core is a little bit warmer, because it's like, how can liquid exist underneath the ice? That's always been kind of hard for me to wrap my head around. When I was living in Iceland for a winter years ago, I went for a tour inside one of the glaciers, and I learned that inside glaciers there are ecosystems, just like every other ecosystem. And I was blown away, because inside a glacier, you can have rivers of moving water, and you can have lakes of liquid water inside of a glacier. And I just could not wrap my head around how water surrounded by ice doesn't freeze. And that was so fascinating to me to see that. They're like, yep, here's a lake inside of the glacier. And it looks like Titan has that same kind of deal. So is there, do we know if there's any kind of geothermic activity happening? Maybe we could get some bacteria bubbling up from deep within.
I think the thinking is very much that the answer to that is yes. So what keeps the rock of Titan warm is the tidal interactions with Saturn. So you've got this squeezing and squashing, very, very slight in the case of Titan, because it's a big, big world, not anywhere near as big as Saturn, of course. But and so that the tidal effect, as we call them, and it's tides not in oceans but in rock, heats the rocky core of Titan, and to some extent that helps to keep the ocean liquid. Plus the pressure of the ice on top of it. So when you compress a liquid, then you change the freezing point. Plus the fact that it's probably very, very rich in minerals like perchlorates, which drop the freezing point by many tens of degrees. And so it's reasonably easy to understand why you might have a liquid ocean. And it's not just Titan, of course. There are probably about half a dozen worlds out there that we think have this same structure. On at least one of them, and that's Enceladus, another of Saturn's moons, there is evidence of hydrothermal activity because Cassini, one of the most wonderful space missions that was ever carried out, Cassini flew through the plumes of ice crystals that were being squirted out around Enceladus's south pole, these geysers of ice, which did contain molecular hydrogen, and that was seen as symptomatic of geothermal activity at the base of the ocean there. So, you know, that you're probably right. And as soon as you've got hydrothermal vents, we start thinking, oh, yes, living organisms and things being formed using the energy of just the hydrothermal energy itself to form life. And I suspect that's where the scientists who've done this particular research that we're talking about are coming from. The fact that we probably do have this geothermal activity, therefore we probably do perhaps do have living organisms deep in the ocean of Titan. But the downside is you're not going to get the nutrients coming down from the surface through that thick layer of ice on top. It's remarkable stuff. I find, you know, myself being excited about the possibility of future missions to these worlds where we really do start tinkering around and finding out what there is in the oceans underneath. But they might be quite a long way in the future.
Yeah, and how these things could be so similar or maybe so different from life on Earth. Isn't there a theory? Are you familiar with the tardigrade?
Of course, yes.
Yeah, so
Yeah.
you've heard that there's like some people speculate, and I could be totally wrong. Some people speculate that the tardigrade is not from Earth.
I like that idea, and they probably think that because the tardigrade has survived rather well, or some of them, on the outside of the International Space Station. They turn into, there's a name for it. Is it a ton? T-U-N? They turn into a dehydrated ball when they're in an environment that's not their normal environment. They get rid of all the water and turn into this little solid ball of stuff, which is still alive but isn't really doing anything. You know, all the biology that keeps us alive is on pause, and so that is probably why people think that they might come from other worlds. I find that very hard to believe. I think they've probably got a fairly well sequenced genome here in a terrestrial environment, but they are remarkable creatures.
Oh, they're so cute.
And they're very cute, yeah, and 0.5 millimeter long. They're called water bears. You don't have to run away from them because they're 0.5 millimeter. Yeah, they are the poster child of the astrobiology world.
You know, it would be really crazy to think about is hundreds, maybe thousands of years from now, would we finally figure out what's in a black hole? And what if we found a tardigrade in there?
It might be a stretched out tardigrade. It gets spaghettified when it gets near the black hole. But look, tardigrades can turn up in the most unusual places. So you could be right. And yes, go ahead, Heidi, sorry.
No, that's just maybe something to think of. That's what's inside a black hole. We always that is the most popular topic here on Space Nuts is black holes and the real fringe of astronomy, science, and cosmology. But you know, sometimes it's funny to think, you know, a black hole, you know, it's not a wormhole to another dimension. Maybe it's just it's a little playground for tardigrades.
Yeah, it could even be a tardigrade hole to another dimension. You never know. That might be where they came from.
Yeah, maybe the tardigrades are the ones running the whole show. And we should...
Yeah.
Okay, we checked all 4 systems and keying was a go.
Space Nuts.
So while we're talking about black holes,
While we're talking about black holes,
well, it just happens to have come up in the conversation. There is some new work that we think sheds light on one of the big mysteries about black holes, and that is that they seem to come only in 2 sizes. Very big and very small. Well, not really that small. Let me clarify that. So we've got what we call stellar mass black holes, about the mass of a star. In fact, they're more than the mass of a star because a single star like the sun is not massive enough to turn into a black hole, but there are stars which are much more massive than that, and at the end of their lives, the core of the star collapses to form a black hole, and we call those stellar mass black holes. Their masses are typically 10 to 20 times the mass of the sun. And then at the other extreme, we've got these supermassive black holes, which we think populate the center of all galaxies. We think there's a supermassive black hole in the middle of every galaxy. That's a relatively new deduction, perhaps only in the last 10, 15 years or so, including our own galaxy, which has a black hole with a mass of about 4 million times the mass of the sun, sitting 25,000 light years away as the crow flies in the constellation of Sagittarius. So supermassive black holes can extend in mass up to not just millions, but billions of times the mass of the sun. And we know of many examples of that. But the conundrum is that there's nothing in between. You've got the small ones and the big ones, but where are the ones that have 10,000 times the mass of the sun or something like that? And we call these objects intermediate mass black holes. They should exist because big ones and small ones exist. And so the issue has been very much in trying to find them. Where can we find these intermediate mass black holes? And the thrust of people's research has been to look at the globular clusters. Globular clusters are clusters of stars. They're sort of globular or more or less spherical in appearance. Very dense clusters, tightly packed together. The best examples of them, I'm sorry to have to say this, Heidi, but they are in the southern hemisphere sky. Omega Centauri and 47 Tucani, they are brilliant globular clusters, even when seen through binoculars, believe it or not. You don't need a big telescope to see that there's something quite different. But these objects consist of perhaps hundreds of thousands to millions of stars in a relatively small volume. And because the stars are relatively tightly packed in a globular cluster, the insights have been that if you're going to find intermediate black holes, that might be the kind of place to look. Because in a sense, a globular cluster is like a sort of mini galaxy, although it's part of our own, the ones we're looking at are part of our own Milky Way galaxy. But they've got characteristics that are almost as though they were the nucleus of a galaxy whose outer stars have been stripped away, something of that sort. We don't know that that's necessarily their origin. But because people think that these supermassive black holes grow over time, maybe the globular clusters would let you see a sort of freeze-dried version of a galaxy whose evolution has stopped. And so you've got a black hole that's only grown to something like hundreds of thousands, tens of thousands of times the mass of the sun. And so, cut to the chase. I'm sorry, that's a rather long preamble, but you did ask me about black holes. And so the new research that we're talking about, once again, this is clearly a Chinese episode of Space Nuts, because they come from Chinese researchers using telescopes, one of which I had quite a bit to do with, a telescope called LAMOST, which is the Chinese Large Aperture Multi-Object Spectroscopic Telescope. That's what LAMOST is an acronym for. I sat on 2 committees during the early 2000s.
Were you in China?
I was, yes. It was as a guest of the Chinese Academy of Sciences to help them decide how this telescope should be built and what they should do with it. It's a very interesting experience.
How long were you there for?
It was a matter of a couple of weeks each time. It wasn't a long stay, but it was certainly very illuminating. I learned a lot and met some fantastic Chinese astrophysicists and colleagues. We had a great time, actually. It was very, very enjoyable. But to cut to the chase, other instruments have been used by these Chinese astronomers. Chinese Academy of Sciences is the main institution where they're involved. And what they've done is they've looked for stars associated with a globular cluster that have very high velocities, and they found some. And the reason they're doing that is that you can envisage that in the nucleus of a globular cluster, in the heart of this really densely populated region of space, if you did have a black hole at the middle of it, what you might find is stars that have close encounters with that black hole. Now, if these stars are binary systems, that's to say they're in pairs, and actually most stars it's not quite true, about half the stars in our galaxy are in pairs. They're members of binary systems. If you had a situation like that, and a binary pair goes near an intermediate black hole near the center of one of these globular clusters, what happens to it? It gets ripped apart in the sense that one star gets sucked into the black hole and the other is given an enormous boost in velocity that essentially projects it out of the globular cluster. And so they've found a number of stars with very high velocities, including one with a velocity of 550 kilometers per second, which is an extraordinary high speed for a star. That's not just leaving the globular cluster, it's leaving our entire galaxy. It's fast enough to leave the galaxy. And so what they're speculating is that is evidence of that, and other observations that they've made is evidence of there being an intermediate black hole at the center of the globular cluster. And the reasoning, just to prolong this a little bit longer, the reasoning is that in order to find a star leaving at such high velocity, it must have gone through this process of being part of a binary system, and one half of the binary is pulled in, the other gets thrown out. But in order to do that, you need a large mass in a very small space. So you can rule out a dense cluster of stars right at the middle doing the same gravitational trick. That wouldn't work because the cluster would be too big in volume, and so it can only be a black hole. Moreover, the fact that it is not showing itself in any other way, it's not gobbling up stuff and releasing X-rays all the time like the supermassive black holes do. Therefore, it must be something of a smaller mass than a supermassive black hole. And I think these scientists have basically put a figure on the size of the black hole that they think is at the center of this globular cluster. And I can't remember how big it is. It's a few tens of thousands of solar masses. And they've done that by looking at the dynamics of this star that's been ejected. Really interesting piece of work. And perhaps not definitive proof, because we haven't seen it yet, but really good evidence for the existence of intermediate mass black holes.
Wow, that's amazing. I want to circle back to one thing you said. You said it's ejected at moving at, what did you say, 550
kilometers per second.
Per second. What's the average speed of a star for me to have that reference point?
Yeah, so that's right. So it's our motion through the galaxy. The sun's motion is in the region of 200 kilometers per second.
Oh, okay. So more than double.
Yeah, that's right. So this is what a star would have if it's circulating in a kind of well-behaved fashion, as our sun is doing, thankfully, in a well-behaved fashion around the center of our galaxy. That would be a typical speed, a couple of hundred kilometers per second. So something at that 550 kilometers per second is definitely leaving the galaxy. Another project that I was involved with some years ago is a project with the delightful name of RAVE. RAVE was the radial velocity experiment. Meant we could write papers with titles like Rave On and, Raving Mad, all of that. Anyway, the RAVE survey was a survey of the speeds of roughly 500,000 stars in the sun's environment. And we did find outliers within that cohort of stars. I think the fastest we found was 400 kilometers per second. And we interpreted that as stars that had interacted actually with the black hole at the center of our galaxy, because that was where they were coming from, not to do with a globular cluster. But yeah, I was the project manager for RAVE. It was very interesting, interesting project.
Slingshot out.
That's right.
It really is amazing. I mean, thinking today, we talked about the tiniest little things, little microbes, and then the biggest things, these full, big, giant interacting. And that's just one of the fun, delightful parts of space. I think this is a tagline somewhere. Someone's using this. There's space for everyone. Everybody's interests align in space. And whether you are a biologist, an astronomer, cosmologist, a human physiologist, there's a job for you. Everybody can find a place working in this industry. I even saw something that NASA had put out that they have someone working there who's a seamstress. It's like, well, we still need a seamstress
I
to
saw
put
that. Yes.
these
Spacesuits
sails together, the suits and the sails.
And the sails,
Anytime there's textiles involved. So, not everything at NASA and space is STEM specific. I mean, it's obviously heavily STEM, but I just want to remind everyone that if you have interests in these things and you have skills, then you probably can find a place where you fit in. So I think on that happy note, Fred, is there anything you would like to add to today's conversation?
No, I think we've covered pretty well everything. I think what you've just said is absolutely right. When people ask me how they get into astronomy and space, I tell them the same thing. It's STEM heavy, but really there are openings in the world of astronomy as well. Not sure about seamstresses, although big telescopes occasionally need fabric covers and things of that sort. I'm sorry, seamstress is very gender specific, isn't it? Is there a word for?
I don't know, actually. I've never thought of that. It's I guess that is the funny thing about language is I heard somebody the other day refer to the moon as he. And I was like, wait a second, that's wrong. Everybody always refers to the moon in the feminine and the sun in the masculine. And it's like, there's no rule that says you have to do it that way, but that's just the way that mythology's evolved around these celestial bodies.
Let me surprise you. Aboriginal culture here in Australia has a male moon.
Really?
Yeah. It does.
Well,
it's the other way around.
That could be a tangent for another episode then.
Yeah, there's a lot to unpick in that, actually.
Yeah, there's a lot of interesting, if you look at etymology and how that's played in. See, there you go. If you're an etymologist or a linguist, there's a job for you too. All right, Fred. Well, it has been a delight and a wonder. And this is Heidi Campo signing off. I hope you all have a wonderful rest of your day. And thank you for listening to Space Nuts.
Space Nuts. You've been listening to the Space Nuts podcast.
Complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.